have Professor Beylkin, who will talk about quadratures for bandlimited functions and their applications. Professor Beylkin got his diploma from the University of St. Petersburg in former Soviet Union, and his PhD from the New York University. He then spent some time in academia and in industry until he joined the Department of Applied Math here in 1991. He has published tens of articles and is cited in the ISI highly cited researchers list. He maintains collaborations with people in the academia, the industry, national labs, and he's one of the co-PIs of the COSI program. So, thanks.
Thank you for introduction. Okay, so so I would like to explain all these things, but what I find is most people don't know much about these things. So as I go on, I will be asking you whether you understand, and then I can expand a little bit. Probably, I don't know whether we have things to write with, but I'll try to explain it anyway. So I'll start with quadratures. Then I will explain what are the prolate spheroidal wave functions and their role. And then I will switch to an application that kind of probably is useful in inverse problems. Probably because I'm not, we are still developing those. If I don't get to the end, you can look in the papers and finish off. So I prefer to spend time sort of making sure that the basic ideas are well understood. So, all right. I push it. Okay. So let's start. How many of you don't know or know, rather, how many of you know Gaussian quadratures, standard Gaussian quadratures? Okay, so I have my first problem. So, so if you want to compute an integral, right, you want to represent it by a discrete sum, which is on the top here. And if you have m terms, there are two m degrees of freedom. You can choose nodes and you can choose weights. Now, standard approach to obtain Gaussian quadratures is to make this exact for polynomials of degree 2m minus 1, which means that you have 2m coefficients. So there is a match between the parameters here and here if we substitute polynomials instead of f. So w is a weight with fairly mild constraints on it, and it is a well-known fact, and I hope that most of you know that the nodes of Gaussian quadratures are the roots of an orthogonal polynomial of degree m, and the orthogonality is with respect to the inner product, which involves this weight. Okay, so how many people don't know anything about what I'm saying? Okay. Well, do we have a... Yeah, okay, thanks. So I can very briefly outline the way to show it. So orthogonality means that you have polynomials, say Pn, Pm of x, W of x, dx minus 1, 1, delta, and m. So you construct a system of polynomials which behave like this, and then when you construct, basically what happens if you have an integral minus 1, 1 of, now let's call it P of x, W of x, dx. This and this P, calligraphic P, is of degree 2m minus 1. Then by using Euclidean division, if I take orthogonal polynomial from this family of degree m, divide, I get q m minus 1, this is a degree, plus remainder of also degree m minus 1, right? It's Euclidean division of polynomials. And then if I substitute this into here, I will get an integral minus 1 q m minus 1 p m w of x dx plus integral minus 1 r m minus 1 of x w of x dx. And this is 0 because of orthogonality, because these degrees are definitely different, right? And so, and once you're here, that's what you need to match now. Now, if I do this now in the discrete manner, so I replace this by a sum, so I have a sum, so this integral I want to approximate it by a sum over m from 1 to capital M, and I substitute this, I get q m minus 1 of xm pm of xm plus r minus 1 of xm, and I need to add weights, w m, and let's write this sum separately. Okay, if I do that, then if I select xm's, so this piece is vanishing, I achieve the same as what this thing does. And then I just need to match this 2, which is now a linear problem. Okay? So if you look at this, if I do a discrete sum, because of the, and then select these nodes to be the roots of this orthogonal polynomial, then I achieve the same thing as this piece. And matching this 2 is easy because now my degree is m minus 1. It's exactly the right number of variables. Okay. Well, so this is the classic Gaussian quadratures, and it looks wonderful. There was time in the 80s when it was reinvented every couple of years. However, now let me describe how it's used. Well, if f on this interval, a function, is approximated by the polynomial, then you can, in this form, I mean this is the error, L infinity, then integrating f using this quadrature, you get very decent error. Okay. Notice that in practical use you always have some error. Oops. Okay, so everything is great, except that if you start looking in particular cases, for example, Legendre polynomials, which is weight 1, you will notice something that is very unpleasant, that the nodes of the quadrature concentrate tremendously towards the endpoints. Heuristic reason for that is that polynomials in principle can grow rapidly near the boundary, and you need a lot of nodes to capture the worst case scenario. Okay? So this is the classical quadratures. And an alternative that was developed much more recently is the same problem. We have a weight, but now we will try to make it work for functions which are exponentials, or sines and cosines. Now the reason it's more interesting is because in most cases these are the elementary building blocks. For the same reason Fourier transform is an interesting object and so on. Now, but you see, B here is any number by absolute value less than C. So number of these functions is infinite. Unlike in the previous case, we were trying to approximate things on a subspace of finite subspace of polynomials. Here the number of functions is infinite, so there is no way to make it exact. On the other hand, the way we use quadratures, we never really care whether it's exact for actual function. It's always approximate for functions that we're interested in anyway. So we can ask the question, can we do it with some finite accuracy? And the answer is affirmative, that indeed you can. So currently there are two methods for finding these nodes and corresponding weights for a given accuracy and given bandwidth. C, by the way, is called bandwidth in the previous slide. So one method is due to Xiao, Rokhlin, Yarvin, published in 2001 in Inverse Problems. But the method works only for the weight 1. The reason will become a little bit clearer later when I explain what prolate spheroidal wave functions are. And with Lucas Monzon, about the same time, we constructed a method to develop these quadratures with more or less arbitrary weight. Okay. So I will give you a brief idea of what the method involves for finding those nodes and weights, and then I will outline the properties. And for people who do practical computations, this is much more the properties are more important than the method by which they derive, but because in the end you get a table. Okay. All right. So we consider integrals like this. So this is the weight, and for a given band limit and given accuracy, we want to approximate this function. So you see we're integrating over theta, but x is anything in the interval -1, 1. C, you can think of C as a large number. This is your band limit. And we want to approximate it using this sum. And we want it to be valid for all x. Okay. So then it allows you to think of it as a quadrature. But now it's a quadrature that works for the whole interval in x. Okay. So this is our goal. This is what we want to do. And the way it's done, so without explaining why it is done, I will just give you a sense of the algorithm. So we take this integral and discretize, instead of x we put k, but the way we do this, we oversample the function u of x by, say, factor of 3. This is typical. And you get a Toeplitz matrix. And then we look for eigenvectors of this Toeplitz matrix corresponding to small eigenvalues. And the size of the eigenvalue gives us the error of the resulting quadrature. So we can select it's more like quantum mechanics. You have discrete values, so you need to find the eigenvector corresponding to some small eigenvalue, and the eigenvalue gives you the accuracy. And from eigenvector you construct a polynomial, find the roots of it, and that gives you the necessary discrete values of the exponent for these quadratures. So why is it so is involved, but let me just give you a brief explanation. Well, these are just properties. I don't want to go into that. Essentially, it's based on this formula, that if you have the integral where this is Laurent polynomial, which is like Fourier series, right? Then you can write it as a discrete sum plus another integral multiplied by the eigenvalue. And if this eigenvalue is small, you can cross this out, and this is your quadrature. This is basically the idea. And it turns out that if lambda is simple eigenvalue and all roots are on the unit circle, as most of the time they are, then this set will contain positive and negative numbers, and I will illustrate that. And there are some other properties that also an interesting statement about the structure of Toeplitz matrices, that you can represent Toeplitz matrix in the form which is more like SVD, but the components are Toeplitz matrices themselves. So it's this is again something technical that I'm not going to go in. So here's an illustration. So let's take weight 1. We oversample, so we're looking at this interval only. So band limit is 15 pi, and this is the eigenvector corresponding to the eigenvalue, 30th eigenvalue of size 10 to minus 16. Now, you think from this picture that function is 0 here. Well, it's not. This is how it looks. And these intersections are actually the nodes of the quadrature. So, oops, wrong button. Okay, so this is, they happen to be on the unit circle in this case. This is the allocations. And now let's look at the weights. So this is like nodes outside of the interval, right? And these are nodes inside. It's a bit strange, but if we look at the weights, you'll see that nodes outside have tiny weights with a minus sign. Of course, they will be thrown out. You don't need them. And weights inside are reasonable. And there it goes. So you get it through this kind of mysterious computation. Now the position of nodes depend now on two things, on the band limit and the desired accuracy, which is extremely important, I think, for all kinds of practical applications, because you can trade accuracy for bandwidth doing this. So, and this is band limit, and this is number of nodes. And if you look carefully at this formula, there is actually a relation between these numbers. It's clearly linear, but it's actually related in much more fundamental way. I will illustrate it better with a graph later on. Okay? Okay, now you can do the same with weights other than 1. And this one will be useful for us to describe what's happening in the disk. Okay, so this picture is almost the same. It's a little bit different, but these are the positions again of the nodes. Okay, so now, having said that we can do it for various weights, let's look at the distribution of nodes for the Gaussian quadrature. So this is the graph showing the ratio of the distance between nodes in the middle. That's the bottom, to the ratio of, to the distance between nodes at the very end. They do concentrate towards the end. So if you take this ratio and plot against the number of nodes, you can see that it sort of converges to a constant. Now, if the same ratio were done for the classical quadratures here, this will decay as 1 over m. So they don't concentrate excessively. For example, this means that for accuracy about 7 digits, you have like 3 times more nodes towards the end, but it doesn't depend on the number of nodes, which means that I can use these quadratures with any number of nodes, whereas you cannot do it with classical Gaussian quadratures, because the distances will become so small that the benefit that you're using from reducing number of nodes will be totally overwhelmed by the problems, say, with time evolution, with any, with other, condition numbers and everything else. Here it doesn't happen. The other thing is that for Gaussian quadratures, because it's based on approximation by polynomials, you can show that as you increase number of nodes and compare the sampling to the Nyquist sampling for periodic functions, you will theoretically be worse at least by the factor of pi over 2, which is 60-70%. In reality, because you cannot go to large numbers, this ratio is much greater. It's about a factor of 3 for small numbers. So polynomial approximations will never give you anything close to what you get if the function were periodic. So the punishment for having function on an interval is very severe. Okay. It's not the case with these quadratures. Asymptotically, the ratio goes to 1. And it goes to 1 pretty quickly. So if you have, say, 200, 300 nodes, this is, maybe 5–10% over the Nyquist frequency. So if you do interpolation, for example, you can do much better with this if, in comparison, what you can do to periodic functions, which is ultimate sort of efficiency, Nyquist criteria, basically. So here we're asymptotically approaching Nyquist as you increase number of nodes, whereas asymptotic formula for Gaussian quadratures will only stay about here, pi over 2, which is somewhere here. It will never approach 1, ratio 1. Okay, accuracy as a function of number of nodes. So for integration, it's accuracy epsilon. For interpolation, it's square root of epsilon. By the way, this is standard kind of relation that you expect in this case. Okay, so now let's switch topic a little bit, and I'll explain Slepian functions. So, as the abstract says, you cannot have concentration of functions simultaneously in both domains. So Slepian and his co-authors ask the following question. Let's look at the eigenfunctions of this operator. So this is like, now if you do optics, this is finite aperture, one-dimensional finite aperture, right? And if we look at eigenfunctions, it turns out that in this case, you can show that all eigenvalues are distinct. That is simple. All non-zero. If you can arrange them this way, and they're either real or pure imaginary, depending on parity of eigenfunction. And then if you apply the adjoint, then this operator is like this, and you normalize it with this, then these become eigenfunctions of this operator as well, right? And this is just, kind of sinc. And mu's are absolute values squared normalized. And then what happens for large C, the first two C over pi eigenvalues are very close to 1. I will show you similar pictures for the disk, but it means that visually you won't be able to tell them apart from 1. In fact, computer will not be able to tell them. It will treat this as multiple eigenvalues if you were to supply the matrix. And then there is a transition region where about log C eigenvalues decay rapidly to 0. And then eigenvalues become so small that the decay is exponential. Okay, so where this name, it's a very complicated name. Why does it? Well, the paper of Slepian, written in early 60s, they observed that this integral operator that I just described commutes with this differential operator. And if two operators commute, they share the same eigenvectors. So the same function psi is an eigenvector of these differential operators. And it just happens that this differential operator produces functions of classical mathematical physics, which are called prolate spheroidal wavefunctions. So it just happens this way, and that's why this complicated name. And probably as time goes on, this will be probably renamed into Slepian functions. Okay. So basically he discovered that L and Fc commute. And it turns out that this commute happens only when this weight that I was describing before is 1. Otherwise it won't commute. And so this approach I mean, Rokhlin's approach to quadratures was to first compute these functions and then follow more or less classical schema. Instead of polynomials, replace them by these guys. Okay. But it works only when weight is 1, because otherwise you don't have this differential equation. Now, when band limit goes to 0, in this limit, these functions are Legendre polynomials. Because if you cross this term, this is differential equation for Legendre polynomials. And now Chebyshev system, well, basically, if you take orthogonal polynomials, you will observe the following properties: that the first one has no zeros, the next one, 0, 1 has no zeros, next one has 1 0 crossing, next one 2, and so on. Functions with this property, one of the definitions of a Chebyshev system. These functions, these eigenfunctions, have exactly the same property in this interval. Okay. Okay. These are the properties. So, you know, there is this problem that has never been solved. Is suppose you have a function given to you on some interval, and you want to extend it, extrapolate it outside of the interval, right? So if you try to do this with polynomials, you will discover very quickly that you cannot do it in any kind of presence of noise, even if it's truncation of the 16-digit double precision. It simply won't work. You will blow it up. Now, prolates allow you qualified extension. Namely, you compute these functions. So you have a function expanded with respect to these functions on an interval. And then let's see what happens. You can use this formula. Basically, the only thing I did, I moved mu j to the right. I can use this formula to define psi j of x outside of the interval, because here x can be anything I want, right? And let's see how it works. If mu j is close to 1, I have really no problems. So in the region where mu j is 1, I can do it. But as mu j becomes smaller in transition region, maybe I can do it, maybe not. It depends on my accuracy, how much accuracy I have. And then when mu j is very small, it will blow up. So I can do controlled extension, not for all functions, but only for some, which makes perfect sense. You cannot do it with anything else. I mean, this is the only way to do it. If you want extrapolation, this qualified extrapolation can be done only if you use this type of functions. Now, this system of functions is orthogonal on -1, 1, but it also, well, it's orthonormal, the way we normalized it, but it's orthogonal on the whole line. And then there is this formula. So if you have, if you want to write an expansion of exponential, notice that lambda j become extremely small at some point. So you can make it finite with some accuracy, and that works. This is the shortest possible expansion of this kind. There are others involving Chebyshev polynomials and Bessel functions, and that's how you actually get this pi over 2 factor that I was talking about. Okay. Now, having quadratures, we can actually construct approximate prolate spheroidal wave functions by insisting that we construct quadratures for epsilon square, whatever epsilon we want, and then we approximate the kernel this way, and then everything goes discrete, and we can actually compute it. Again, you would be hard-pressed to do it with any other kind of quadratures. Okay. We can introduce spaces of these functions, explain how they sort of relate. Let me skip that. So by going through this, if you take classical band-limited functions, we can show that actually we can use these quadratures to approximate any function from that class. Okay. So here is an example of what you can do. So suppose I give you this function. In this case, it's just cosine cx. But you see, I've chosen the C so that on the interval 1 minus 1, it's not periodic. That is, you can make it periodic, but then you will have jump in the derivative. Severe jump, actually. It's kind of steep, right? So if you try to use Fourier series to approximate this by exponentials, and you want accuracy of how many 9 digits, you will have to have something at least 10 to the 9 terms, because the error will decay like only 1 over the number of terms. Now, using these nodes, and I can achieve this with about 30 terms. Okay, so this is the error of approximation by these exponentials. Of course, this is not periodic function anymore. And you can do it with just about 30 terms, which is quite nice. Okay. This is something that illustrates the trade-off between bandwidth and accuracy. So we take function e to the ibx, and we want to interpolate this function from a finite number of points in the interval minus 1, 1. And b will be changing sort of between 0 and 16 pi. So 32 nodes, and then we start changing the band limit, and we get different accuracies. So if I want 14 digits, I will be very accurate, and notice this is a logarithmic scale, so I have very flat bottom here. Okay, it will be even more transparent when we will look at derivatives, but here is a flat bottom and very rapid rise of error as we reach the limit. With the same number of nodes, if I want less accuracy, I have wider bandwidth. And if I want to give up more, I have yet wider bandwidth. This is the trade-off between, so if you measure in data, say, with 3 digits, you can then achieve the bandwidth. But if you're interested in the answer only with 1 digit, you can have slightly wider bandwidth. You cannot do it with anything else. This is the only tool that allows you to do that. Okay, here's the derivative. So let's look. There is this line, and this is so what we do, we differentiate in sine bx, where b again varies between 0 and 32 pi. And we use different techniques: finite differences, Chebyshev polynomials, and then prolates with different bandwidths. And you will see what happens. So if you use finite differences, in spite of our serious attempt to do this, we were never able to reach double precision. We were always sort of like half of this. The reason is that nodes become too close and you have catastrophic oscillations. You really cannot do that. And so the bandwidth is tiny, as you can see. If you use Chebyshev polynomials, you can reach precision, but 14 digits is narrow. It's better here, but it's kind of slow, fairly slow rise of error, and the resulting bandwidth is not very good. But with prolates, what you get is much wider bandwidth, and again this trade-off. So you have 10 digits, you have this bandwidth, you have 6 digits this bandwidth. If you were to go to 2 digits, you would have even wider one. Okay. Now notice also, you see, when you do problems of wave propagation, you have numerical dispersion, right? So those of you who try to do this will find that, for short time distances, you have to have at least factor of 8 oversampling, and if you want to go long distances, it probably rises to factor of 32 and so on. And even you do that, you lose digits like crazy. And the reason is that if you look, for example, this finite difference type or this one, different frequencies propagate with different velocities as a result of this approximation. On the other hand, these guys are almost flat. So the onset of dispersion is delayed. It's much and we can achieve any accuracy. So, for example, we can start with 12 digits and cross the Atlantic Ocean and be at about 9 digits. So we basically can control accuracy. You cannot do anything like this with finite differences. Okay? Okay, now let's switch to something that is more related to inverse problems. So we want to construct transforms from square in space to disk in Fourier space and back. So I'm talking about Fourier transforms. So you typically go from a box, FFT or DFT rather, gives you transform from the box to the box in Fourier and back, right? There are many reasons to be interested in transform from disks. Okay, so Slepian has a paper where he considered transform from disk to a disk, but it turns out it produces very different results than what transform from square to a disk. So disk, you can think of disk as a circular quadrature, and the square is the screen. So if you do optics, that's how you can think about it. Okay. Okay. So B is the box. So in space we are like this, right? We take Fourier transform over the box and go to the Fourier space, restrict it to the disk for convenience radius 2c, and then map it back to space. So this is the adjoint operator, mapping from the disk to the box. And we consider the combination of them. And that can be cast as a convolution with a kernel. And this kernel is now this. Okay, Bessel functions. And if you do optics, you should know this particular guy, right? Now, functions in space live on a square. So this is what. So we want to consider this eigenvalue problem. Complete analogy with the original Slepian, except that what he did for this two-dimensional case, he mapped from disk to the disk, and this is square to the disk and back. Okay. Okay, just slow because these are big pictures. It's coming. Okay. Well, if we compute these eigenvalues, that's what we get for this mapping. And this is drastically different from if we were to consider disk to disk. So these are this analog of this muse in one-dimensional case. And you can see again that they are very close to 1. Graphically, they look like, flat, but they are all different again. Then there is this transition region, again of logarithmic size given the bandwidth. And then it's 0. Now, this null space is quite large because you will see in a second why. Well, the reason is that in Fourier space we have a disk. This is the Fourier space, these pictures. So these are the West eigenfunctions. So this is the eigenfunction corresponding to the smallest eigenvalue. And then the next smallest, the next smallest. And if you look at them, you cannot work with them, basically. So these are your enemies if you want to do something. So you see their Fourier transform is concentrated in the corners. And of course, the disk is inscribed. So, of course, you cannot see those. Right? So these are how they look in space. It's like a Nyquist kind of a chessboard, quite suppressed towards the endpoints, boundary rather. Okay. How do we construct quadratures now? Well, we use separation of variables, again, this is better, if you read the paper, it's easier to understand reading than looking at this. But remember, we know how to construct Gaussian quadratures for exponentials, so analog of Gaussian quadratures for exponentials. And I showed you an example where the weight was this particular weight. So this is exactly what is done here. Then this kernel now is discretized this way. And then these are how these quadratures look like. So we didn't tell the algorithm that it's absolute value of rho, but it knows how to put them together. And this guarantees accuracy and everything. So people, for example, who know X-ray tomography, a similar filter exists there, which is usually approximated by Shep-Logan. But you can do it very, very nicely with guaranteed accuracy, whatever it is. So, and then, well, again, so you can do inversion only if you're sitting on the part of the spectrum where values of mu are 1 or a little bit below in the transition region, but not very far, right? Because everything else is like numerical null space or so disturbed that it will cause problems. Okay, so this explains that. So this is computation where ideal conditions. You have a function sitting in the square and reaching 0, practically 0 near the boundary. So we transform it to the grid in the Fourier space on the disk and then rotate it. Actually, rotation, we don't do anything. We just rename this radial diameters and go back, and we get this. So basically it's rotated as it should, and we achieve accuracy of 11 digits. And intentionally we took some strange looking angles. It can be any angle, whatever. The main point here is that we guarantee accuracy in all these computations. So now this is a harder case. So this is the function, and here is inversion, which I didn't describe how, but it's inversion from the functions which have mu very close to 1, and this is from the transition region. And you see that functions with mu close to 1, as they should, they mostly concentrate in the interior, and the functions in transition region actually are responsible for the boundary. And the reconstruction, we can handle it. So you see, if you try to do this function with just FFT, you will not be able to, because it's not periodic. You'll have terrible problems. This is the error that you get. Okay. Finally, Ewald limiting sphere. So people in optics should know what that is. If you do measurements with 2 unit vectors, incoming and outgoing, say in Born approximation, you get Fourier transform of your object measured at k nu plus k mu or minus k nu, whatever your sign convention is. And basically you measure on the circles, and they're rotated around. So if you take these circles and discretize them with equally spaced angles, both of those, you will be surprised to find that all the nodes line up on the diameters. Okay? It was not discretized in the radial directions. It was discretized in the secular directions. In fact, in this case, these quadratures are Chebyshev nodes. So I observed it a long time ago by just playing with this. It's very hard to sort of discover it analytically. But once you know that this is the fact, showing that this is the case is easy. So there are 2 cases, odd and even actually is more interested. They're also on the diameters, but there are 2 there is a shift between them. Okay, so again, these both are discretized on circles running through the center and touching the edge. So now, unfortunately, quadratures based on these discretizations are not very good because you have a singularity at the origin. Well, you can still use them, but they are really not so terrific. Well, it turns out that it's n log n operation to resample it to the quadratures, which are these optimal quadratures I was describing before. And after that, you don't lose digits anymore. Okay, so this is this piece. Again, I'm skipping details, but you know, this is all kind of sitting in the code mostly. Okay, now if you have spatial circular, so you have a cylinder and you want to discretize the support of the cylinder, then you can have embedded quadratures. So these are two quadratures built hierarchically in a very funny way. Yeah, I'm almost done. Okay, so I'm done. So what we're working currently on using these transforms in practical algorithms. So it's not an obvious task, and the impact is not entirely clear, mostly due to the fact that the measurements are have such a low precision, like 2 digits, and with 2 digits you can do various things and not notice that you're doing something wrong. Basically, that's what it is. In fact, you're doing something that is not so bad, but of course you can't control accuracy. So, like if you have few hundred nodes and you have only 2 digits, you can almost pretend that this sequence of samples is periodic. And if you do a little bit of fiddling near the edge, you can really do it quite well with, say, cosine time transforms and things like that. Now, but if you have 15 nodes, then you won't be able to do anything. And with this you can. Also, if you do this for 200 nodes, you will know exactly the accuracy with which you are working. Whereas in the sort of standard case you won't. So, one of the possibilities is to reduce the area in the Fourier space that is needed to collect the MRI data, which will shorten the time of collection. In electron microscopy, it will probably produce entirely new type of algorithm. Well, X-ray tomography, probably we can do very well. I'm hoping to get algebraic type reconstruction algorithm, but not doing any kind of algebraic reconstruction by just directly, because all integrals are computed very accurately. We're working on 3D extension of this. The difficulty is discretization of the sphere, so I have something else that we're doing there. We're constructing quadratures on the sphere which are invariant under dihedral groups, discrete groups. So currently we're working with icosahedral group. So that will allow us to nicely generalize what I just described to you, mapping a cube into the ball into the Fourier space in 3D. Directional bases, which are suitable for numerics. For image processing, there are curvelets, but if you try to use them for numerics, I think you will die before you achieve something. And very difficult, outstanding problem is to construct optimal grids on more or less arbitrary domains. That will have very, very serious impacts, but it's also a very difficult problem, so I'm not going to talk about it at all. So I stop here.
We have time for a couple of questions.
Go ahead.
So you said, are there fast algorithms for calculating these
For this stuff?
functions?
Yeah. So let me explain the situation. So I showed you this transition regions. If you have to include them, then currently we don't have I mean, theoretically we have a fast algorithm, but in practice we don't. If you can manage to be mapping only on those mu's which are close to 1, then we have a fast algorithm. The reason is that there is so-called unequally spaced or non-equally spaced fast Fourier transform. Basically, you have random nodes in space or Fourier space, doesn't matter, and you have trigonometric sum involving them. You can still compute it in n log n. FFT requires you have equally spaced grid. Unequally spaced FFT doesn't. In 1D it's about, let's say, 3 times slower, maybe a little bit less. It depends on accuracy. In 2D it's 8 times slower for single precision, maybe 12, 16 times slower for double precision accuracy. So you can always do that. And the moment you have n square log n type algorithm, you're in business. So as long as we need to do only the adjoint transform, we can do it. There's no problem. So we have fast algorithm. For transition region, we have to do something with eigenfunctions themselves. If you supply these eigenfunctions, we have a fast algorithm because there are only log of them. We can do it sort of in a dense way and everything will be fine. But computing them is a big problem. We don't know how to do it fast. So for small sizes we can, for large sizes we can't. But it looks like in many problems you can do it just with adjoint. It requires a little bit of oversampling usually.
Do the functions differ from the Rokhlin functions? I know they are different, but do they look similar?
Well, I should have put some pictures of them. What happens is that the first function is just a bump. Then they sort of start slowly to oscillate, but they all die towards the boundary. And they can be extended if you need to. As you keep going, they become more and more oscillatory. And they have nice symmetries. I mean, it looks pretty. I mean, and then as you get into the transition region, they begin to have substantial stuff near the boundary. In space, they're on the square. So they're different. So two-dimensional case. Let me explain briefly why is it that disk-to-disk mapping that Slepian did, that doesn't work well. What happens is that for each angular frequency, it's done by separation of variables. So for each angular frequency, you have a radial problem, ODE. And for this particular angular mode, you do get the same kind of thing, flat and then transition, which logarithmic number of terms. But then you have n of such frequencies. So you have n log n transitions. So out of n square, n log n is a transition region. So you don't have this flat piece to work with. And that's the end of it. So they're useless and they were never really used. Whereas this has a substantial chance of being, practical. And it relates to, all it is, it's a circular aperture and a square screen. Because that's a Fourier transform. So how to use it in optics at this point, I don't know.